Okay, welcome to the last session. I'm Arindam Ghosh, I'll be chairing this. The first talk will be by Professor Ajit Balram, and Ajit is going to talk about fingerprints of composite fermion lambda levels in scanning tunneling microscopy.
Okay, so let me start off by thanking the organizers for putting together this very nice workshop and for inviting me to speak here. So I'm going to tell you about scanning tunneling microscopy in the quantum Hall regime, in particular in the fractional quantum Hall regime. This is work done in collaboration with Zlatko Papic's group at University of Leeds, Nicola Renew, Mike Zalatil at Berkeley, and experimental colleagues at Princeton, Ali Yazdani's group in particular. And I'd like to thank generous funding from the Science and Engineering Research Board, a Royal Society exchange grant that I share with Zlatko, and a special mention to the coding package DICAM that we have used extensively for our numerical calculations. Okay, so the plan of the talk is as follows. I'm going to give a very quick introduction to the quantum Hall effects, a quick introduction to integer and fractional quantum Hall effect. And I'm particularly going to focus on the fractional quantum Hall effect in the lowest Landau level, which I'll show can be explained using what is called the composite fermion theory. And then I'll come to the main part of the talk, which is discussion of the scanning tunneling microscopy of FQHE states in the lowest Landau level. So there are a couple of things that I would like to tell you right away. One is that there is a complementary paper that was written by these people, Gattu et al. This is Maitreya Gattu, Srijit, and Janendra Jain from Penn State. And their results are very similar to us. So we actually did a joint posting on the archive. And very recently, there has been a different approach from what is called the Chern-Simons theory, where again, this STM signal has been extracted by these two people. And that I'll not be able to tell you about. And then I'll end with some conclusions and outlook. Okay, so the field of quantum Hall effect was started with this amazing discovery of Kloshwan-Klitzing's, where he took a two-dimensional system of electrons, placed it in a strong perpendicular magnetic field, ran the current one way, measured the voltage the other way, and looked at this ratio of this voltage, transverse voltage to the longitudinal current, the so-called Hall resistance, and found that the Hall resistance was exquisitely quantized in units of h over e square. So there's this plateau at 1, 2, 3, and so on. And the amazing thing about this discovery is that it does not depend on details of the sample. Like whether you have samples as different as gallium arsenide, graphene, and so on, you get the same effect. What kind of disorder you have in the sample also doesn't matter. What kind of geometry you put in the sample also doesn't matter. So it's a very topological and very robust phenomena. And actually from about 3 years ago, this has gone into the standard of units. So the Klitzing constant and the Josephson effect pin h and e for us. So Klitzing constant gives you h over e square, and the Josephson effect gives you h over e. So how do we understand the integer quantum Hall effect? The integer quantum Hall effect is fairly easy to understand. It just arises from primarily non-interacting physics. So in zero magnetic field, electrons just line up to form a Fermi liquid. And in the presence of a magnetic field, this Fermi liquid splits into highly degenerate bands called Landau levels. And whenever you have an integer number of these levels filled, there is a gap to excitations. So here is an example of 3 fill Landau levels. So you just occupy the lowest 3 Landau levels. And whenever you have this gap, you get this quantized Hall effect. So throughout this talk, we're going to work with what are called wave functions, writing down microscopic wave functions in coordinate space. So this is complementary to what is usually done in many body physics, that you're not going to write down some field theory. So we're going to write down some simple wave functions. So let me give you some simple examples of that. So the best example to keep in mind is a state called nu equal to 1, where you just fill the lowest Landau level completely. So it's only this Landau level that's completely occupied. And the wave function for this can simply be written by just appealing to the Pauli exclusion principle. So every electron is parameterized by a coordinate which I call z, which you can write down as a complex number, x minus iy. And every electron has to see a 0 at every other electron. And lowest Landau level wave functions are polynomials in z. So using these two facts, you can write down the wave function of one fill Landau levels. That's just product I less than j, zi minus zj. So this is also called the Jastrow factor. And aside from that, there is this factor of Gaussian, there's a Gaussian factor which just comes from standard Landau level physics. And throughout this talk, this factor will play no role, so I'm going to just ignore it. So we'll primarily be focusing ourselves on this polynomial in z. So one curious fact is that other than this wave function of one fill Landau level, there is no closed form analytic wave function for any other fill Landau level. So if you can write down a wave function for 2 fill Landau levels by constructing a determinant, but it's not possible to write it down in terms of the coordinates. That's an interesting fact. Okay, so very soon after Klitzing's discovery, Sui, Stormer, and Gossart made better samples, went to much larger fields, and found that the Hall resistance in their case was quantized in fractional units. So the h over e square was, the denominator is now multiplied by a fractional like 1/3. So this is the famous 1/3 plateau. And phenomenologically, this looks very similar to the integer quantum Hall effect in that you get a quantized Hall plateau and a vanishing longitudinal resistance. So again, there is a gap in the system, which is why the longitudinal resistance vanishes as you go to lower and lower temperatures. And Sui seems to have remarked that he saw quarks in a condensed matter system, but quarks are not at all relevant here, right? This is all a milli-electron volt phenomena, and quarks occur only at very high energy scales. Okay, so FQHE is actually a really hard problem because fractional quantum Hall effect arises completely from electron-electron interactions. So for a theorist like me, there is a nice limit to take where you send the cyclotron frequency to infinity. Then all the physics is entirely confined to the lowest Landau level. And now what you have is that you have some orbitals in the lowest Landau level and a fewer number of electrons. So here is an example of filling factor 2/5. So I have 10 orbitals in the lowest Landau level and 4 of them are occupied. And in the absence of any interaction, there is huge degeneracy, right? There is 10 choose 4 degeneracy here. And if you take the number of electrons to be very large, then at a fixed filling factor, you get n choose n over nu degeneracy. So that's huge amount of degeneracy. But we know that there is a gap ground state. So what we have ignored till now is Coulomb forces. And there are always Coulomb forces because electrons are charged particles. And the thing that happens is that Coulomb interactions picks one unique state from this highly degenerate manifold. Okay? And quantum mechanics, I mean, this Hamiltonian looks very classical, but quantum mechanics in this problem is built by this lowest Landau level constraint. So once you have electrons living in the lowest Landau level, the positions of the particles don't commute. So x comma y is like I times magnetic length square. That's the only length in the problem. And as I said, interactions are going to pick one unique ground state from this highly degenerate manifold. So if you look at this problem, this seems like a scary stuff because we don't even know how to solve 3 particles interacting with each other. So what hope do we have of solving like an Avogadro number of particles interacting with each other? So the first progress in this direction was made by Laughlin using this so-called Feynman method or the Greek method where you guess an ansatz and then check whether that ansatz is correct or not. So Laughlin guessed this so-called Laughlin wave function where you take the integer quantum Hall state at nu equal to 1 and raise it to some high power like m. So he assumed that electrons are pairwise correlated, and some motivation for this came from this fact that electrons are interacting Coulomb-wise, so that's a pairwise interaction. So electrons, he assumed, always are correlated in this Jastrow or pairwise form. For a wave function of this form to be a fermionic wave function, m has to be an odd integer. Because if I exchange 2 fermions, I have to get a minus sign, and that will only happen if m is an odd integer. So Laughlin actually went on to do more. He actually showed that this state, the excitations of this states are quite exotic. They are actually so-called anyons, and they are actually fractionally charged particles. So if you look at the quasi-particle or quasi-hole of this state, then it carries a charge which is E over m. And then Arova, Schrieffer, and Wilczek showed that if you take 2 of these anyons and braid them, then the phase that you pick is like 2 pi over m. Okay? So very soon after Sui, Sommer, and Gossard's discovery, people made better samples, went to much larger fields, and they saw a whole zoo of fractions. And these fractions primarily occur along this sequence, n over 2p n plus minus 1. So this is the 1/3 plateau, then there was 2/5, 3/7, 4/9. And in a given Landau level, you have the symmetry called particle-hole symmetry, where you can exchange electron orbits to hole orbits. So every fraction at nu can be mapped to a fraction at 1 minus nu. So for example, the state at filling factor 2/3, you can view that as a 1/3 state of holes. Okay, so throughout this talk, we are going to be only concerned at fillings that are less than half, because the fillings that are greater than half, you can just get by particle-hole symmetry. And particle-hole symmetry is going to be a good approximation when the field is large, because then things are all confined to the lowest Landau level. Then you can just exchange electron orbits to hole orbits. And the problem with describing fractions like 2/5, 3/7, and 4/9 is you can't go and put m to be like 5 over 2 or 7 over 3 or 9 over 4, because m has to be an odd integer for the state to respect fermionic symmetry. If you put m as any of these values, then the wave function is not even single value. Right? There's a branch cut if you put like 5 over 2, it has a square root. So again, we are back to square one. How do we go about understanding these states? So progress in this direction was made by Jan, who noticed this fact that I mentioned earlier, that phenomenologically the integer quantum Hall effect and fractional quantum Hall effect are very similar. You get a quantized Hall response and you get vanishing longitudinal resistance, so a gap ground state. So he proposed that the fractional quantum Hall effect of electrons can be understood as the integer quantum Hall effect of certain emergent objects called composite fermions. So a composite fermion by definition is a bound state of an electron and an even number of vortices. And vortices in many contexts behave like flux quanta. So you can also think of a composite fermion as being an electron bound to an even number of flux quanta. And here is the golden path to go from integer quantum Hall effect to fractional quantum Hall effect. You start with electrons at a small magnetic field. Then to each of these electrons, you bind 2 fluxes to turn them into composite fermions. And then what you do is that you slowly smear this flux and merge it with the external magnetic field. And that brings you into the fractional regime, because the fractional regime is one where electrons see a much larger magnetic field. That's why you're at a low filling compared to integer filling. And in this process, you hope and pray that the gap does not close, so that you can adiabatically connect all the way from integer quantum Hall effect to fractional quantum Hall effect. And this adiabatic assumption is questionable. So for all interactions, it's not true that adiabaticity holds. But for everything that I'm going to say in this talk, this assumption is going to hold. Okay, so now with this assumption in place, what you can do is run the tape backwards. You start with electrons in a very strong magnetic field. Now from this external magnetic field, you capture 2 flux quanta and bind to each of these electrons to turn them into composite fermions. And now what you do is that you assume to the lowest order that these composite fermions are non-interacting objects. Okay, just you do like a free fermion approximation. And just like electrons in a magnetic field, non-interacting electrons in a magnetic field form Landau levels. Non-interacting composite fermions in this small magnetic field, which is called the effective magnetic field, form their own Landau-like levels. Okay? And these levels are called lambda levels. And whenever an integer number of these levels are filled, you get fractional quantum Hall effect of electrons. Okay. So this theory also allows you to connect quantities of electrons to quantities of composite fermions. So all start quantities are composite fermion quantities. So the effective field seen by composite fermions is the external magnetic field minus 2p fluxes that you bound to each. Then the thing that would play a role in majority of this talk is this number called the filling factor, which is the ratio of the density of electrons to the density to the magnetic field. This rho phi naught by b. So now you can use this relation to relate the filling factor of electrons to the filling factor of composite fermions, right? Because nu star is rho phi naught by b star. And that tells you that nu is nu star over 2p nu star plus minus 1. And when you set nu star to be n, you get precisely these fractions that we saw, n over 2p n plus minus 1. So that gives you some inclination for why in the lowest Landau level you get fractions of this particular form. So there is also this famous odd denominator rule that also comes out from this theory naturally. So let me pictorially tell you what the states are. So firstly, if you fill one lambda level of composite fermions, you're going to get something that is identical to the Laughlin state. So that I'm going to show in a couple of slides. Now for 2 fill lambda levels of composite fermions, you get the 2/5 state of electrons. And then for 3 fill lambda levels, you get the 3/7 state and so on. So once you establish this mapping to integer quantum Hall effect, things are very simple because we know how to do things in integer quantum Hall effect. Because integer quantum Hall effect is a non-interacting theory. So that we know how to do exactly. So we don't need to necessarily stop ourselves at ground states. We can also construct excitations because we know how to construct excitations in the integer regime. So for example, a charged excitation in the integer regime is the so-called hole state, where you have a missing particle in an otherwise filled Landau level. That now in the fractional regime translates to a composite fermion hole. Now a particle excitation is a extra fermion in an otherwise empty Landau level. That in the composite fermion language is a composite fermion particle. And now you can get neutral excitations by putting these two together. So a particle hole pair, which is called an exciton, now in the fractional regime will be a composite fermion exciton. Okay. So everything I said up until now is fairly qualitative. So one can ask, can we get some numbers out and then check against numerics or experiments? And you can do that. And that proceeds by the constructions of these wave functions, which are called the Jan wave functions. And the way these wave functions are constructed is as follows. So first you construct an integer quantum Hall state at filling factor n, okay? N or minus n. So minus n is just integer Hall state n complex conjugated, that's all. And now to this integer quantum Hall state, you bind 2p vortices, and that is done using the Laughlin-Jastrow factor. So I take this product I less than j, zi minus zj to the power 2p. So this binds 2p vortices because if I now take a zi around a zj, then I pick a phase which is 2p times 2 pi. And if you go around a vortex, you pick a phase which is exactly 2 pi. And because I'm going to work in this limit where the magnetic field is sent to infinity, I have to brute force project this state to the lowest Landau. Okay, so that is what this PLL does. It's a projection operator. So first, let me show why the one fill lambda level state of composite fermions is the same state that Laughlin wrote down. That's because we saw that phi 1 is exactly product I less than j zi minus zj. Okay, so when n is 1 and you take the plus sign, then you get exactly zi minus zj to the power 2p plus 1. So m that was there in Laughlin is exactly 2p plus 1, and that's an odd integer. And there is no need to project because it's already a polynomial in Z. You don't need to do any more projection. One curious thing about this wave function is that although it's constructed as a trial wave function, it has no adjustable parameters. So our usual strategy when we construct variational wave functions is we allow some variational parameters in these wave functions, which we then optimize with respect to some interaction. Let's say you want to minimize the Coulomb energy for that wave function, or you want to maximize the overlap of the Coulomb ground state with that state and so on. But here that is not available. So the moment you fix the filling factor on the left-hand side, everything else on the right-hand side is completely fixed. And these are all some integer numbers. So n is an integer, 2p is an integer, so there is no room to maneuver. So these are variational wave functions with no adjustable parameters. So either they're going to be very good or they're going to be very bad. Another important thing is that these wave functions can be evaluated for very large system sizes. So that looks a bit puzzling because usually if you have to do something like projection to the lowest Landau level, you have to expand the state in all Landau levels and then retain the part in the lowest Landau level. And that's really hard to do because the Fock space of Landau levels increases very quickly. The Hilbert space grows exponentially. So then doing this expansion is hard. But there is a trick, and that's technically hard for me to explain, but take my word for it, there's a trick to directly construct states in the lowest Landau level, and you can do this construction for like hundreds of particles. So this will be important for us because we're going to try and go beyond exact diagonalization, and for that we're going to use this fact that these states can be constructed for very large system sizes. Okay, so some of you probably already noticed that the simplest fraction possible, namely filling factor 1/2, there is no fractional quantum Hall effect. So why is it that there is no FQHE at filling factor 1/2? This again is explained by the composite fermion theory. So what happens at magnetic field corresponding to filling factor 1/2 is that the composite fermions absorb all of the external magnetic field. So they themselves see zero magnetic field. Now in zero magnetic field, just like electrons form a Fermi C, which is a gapless state, composite fermions form their own Fermi C in this zero effective magnetic field. And that state is called a composite fermion Fermi C. So one should step back and think about this a little bit carefully. So in the usual Fermi C that we study about in solid state physics, kinetic energy plays the most important role. And then you do interactions in some perturbative form. But in the composite fermion Fermi C, there is no kinetic energy at all. Like everything is residing in the lowest Landau level. So kinetic energy is completely quenched. So this is a Fermi C that arises completely from interactions. So it's an exotic state which is believed to be a non-Fermi liquid, but there hasn't been any like telltale sign of non-Fermi liquid behavior in this yet. Okay, so now I'm going to go ahead and tell you how good the composite fermion theory is, whether it works or not. So for that, one has to make some choice of geometry. So one has to pick up some geometry, do exact diagonalization, compare the gen wave functions, and see whether they're good or bad. So what I'm going to do is to pick the so-called spherical geometry. And the reason for that is I'm going to focus primarily on bulk properties. So in bulk properties, it's good to consider geometry which is compact. Because if you, let's say, take a planar geometry like disk and so on, then you have to impose some confinement to keep electrons within some distance. Right? Otherwise, if you just have repulsive interactions between electrons, they will all fly away to infinity. So you have to put some confinement to keep them. But in a compact geometry, you don't have to worry about that because it's a compact geometry, electrons have to live within the space. But to construct the spherical geometry, you have this unenviable task of grabbing hold of a magnetic monopole and placing it at the center of the sphere. But for a theorist like me, that's very easy. So you just get a magnetic monopole and place it at the center of the sphere, and that produces a radial magnetic field, which is exactly analogous to the perpendicular magnetic field in the z direction that you get in the planar geometry. So it's essentially the planar geometry wrapped on the surface of the sphere. That's all it is. And appropriate to this geometry, the orbital angular momentum and its z component are good quantum numbers. Because we are going to focus on Coulomb interactions, which are spherically symmetric. So they're going to maintain these quantum numbers. Because this is somewhat technical detail that the flux and the filling factor and the number of particles are not directly related as on the plane. There is an offset, which is called the shift. And that shift is a useful quantum number that characterizes the state. Okay, so the other ingredient we need is how to characterize the interaction. So again, this was done by Haldane, who showed that two-body interactions can be parameterized. In general, any k-body interactions can be parameterized in terms of what are called Haldane pseudopotentials, which are energies of two particles in some relative angular momentum state. So you place two particles in the lowest Landau level in some relative angular momentum state and ask what is the energy of that. So if you have Coulomb interactions, then you get this sort of decay. So as you keep the particles close together, their energy is high, and then it decays in this typical 1/r form. Okay, and throughout this talk, I'm going to assume single component, fully polarized electrons. So only the odd pseudopotentials are going to be important. Okay, so now one can go ahead and do exact diagonalization for small systems, like 15 particles for 1/3, 11 particles for 1/5, and so on. So as you go to lower and lower fillings, you can do exact diagonalization only for smaller and smaller systems. So for 15 particles at 1/3, the Hilbert space is about 2 billion. And the overlap of the exact Coulomb ground state with the Laughlin state is like 99%. I mean, this is a remarkably high number. Because if you just take a random vector in this Hilbert space of 2 billion, the overlap will essentially be 0. Right? And for 15 particles where the Hilbert space is like 2 billion, the overlap is like 99%. So I have a wave function which has no variational parameters, and it captures a superposition of 2 billion coefficients almost exactly. Okay, so same thing happens for 1/5 Laughlin state, 2/5 Jan state, 3/7 Jan states, and the overlaps are almost like 95% and above. So what about excitations? So we saw that the ground states are well represented. Excitations are also very well represented. So here is a typical example. So I picked 3/7, but you can pick any fraction, 1/3, 2/5, 3/7, anything. And you essentially get replicas of these sort of plots. So the ground state here is 3 fill lambda levels of composite fermions. The first excited state is the so-called composite fermion exciton. It's a particle hole pair of composite fermions. And depending on where you place the particle and hole, you get this dispersion. So in this plot, all these lines come from exact diagonalization, and these dots are energies of the composite fermion trial wave functions. And essentially, the dots are right on top of the lines. And the thing to appreciate is that each of these dots is a superposition of like 1,000,000 coefficients. And the dots capture this superposition almost exactly, even though they have no variational parameters. So you just construct one particular state, and it captures a superposition of 1,000,000 coefficients almost exactly. And this is known to be true to up to like at least like 4 or 5 bands. So this is like the ground state band. This is the first excited band, second excited band, third excited band, and so on. Okay. So if there are any burning questions, this is a good time to take them. Otherwise, I'm going to move ahead and tell you about STM. Everything I said up until now is just background stuff. So, okay, so if there is nothing, so let's go ahead and jump on STM. So the question that one should first ask when you learn about something new is, why do STM now? Like, what is special about doing scanning tunneling microscopy? So there are 2 main reasons. One is that the system of choice for a long time in the fractal quantum Hall regime was the semiconductor heterostructures, gallium arsenide, aluminum gallium arsenide, where the 2-deg is hidden deep inside. So reaching the 2-deg was a very difficult task. So doing STM on these 2-degs was extremely challenging. But as we know, in the past decade and a half, the system of graphene and other van der Waals heterostructures have come up. And extensive FQHE has been observed in these exposed samples. So these samples are really exposed to air, so it should be much easier to do STM on these samples. Secondly, the other thing that has improved is in tip quality. So these secrets are somehow not shared, so I can't tell you why the tip quality has improved, but take my word for it, the tip quality has improved a lot. So now people can do STM with a localization length of less than a magnetic length. In a very non-invasive way. So you don't ruin the 2-deg at all, and you can do tip which is very localized. So you can tunnel electron in a very localized space. So the other thing you should ask is, like, what is special about doing STM in terms of, like, you have other measurements of Hall, right? Like other measurements in fractal quantum Hall regime, like you measure transport. So what transport does is it captures the features of quasi-particles and quasi-holes. So in transport, when you do the measurement, you separate the quasi-particle to the drain and you put the quasi-hole at the source. But what we will see here is that STM actually probes the high energy regime. So quasi-particles and quasi-holes are the low energy excitations, and that's what transport and other probes measure. But STM is going to measure the high energy spectrum of the quantum Hall system. So what does STM measure? So up to certain caveats, which I'll come to right towards the end of my talk, the scanning tunneling measurement signal is supposed to measure the energy resolved local density of states. So this local density of states can be probed in 2 regimes. One is when you remove an electron from the system, like you eject an electron out of this fractional fluid, or you can add an electron into this fluid. So you inject an electron. And what we are going to do is we are going to inject the electron at a position which is right under the tip, which I call R. Okay, so this local density of state is a function of both the energy, so you can give some bias to the STM to control what energy you pump the electron in or remove the electron at, and at this position R. So what it is going to do is, if you, let's say, annihilate an electron on the ground state, so omega is the ground state. If I annihilate the electron, then this state is made up of n-1 particles. Or if you add an electron, then this state is going to be made up of n+1 particles. So then you're going to take its overlap with all the exact state in that right particle number regime, and then just sum over this delta function, where the energy conservation is built in. So the thing that is supposedly interesting about STM is that we believe that fractional quantum Hall effect, composite fermions are the main particles. Right? They are the fundamental quasi-particles of fractional quantum Hall effect, whereas here we are going to put in a very high energy electron. So the question to ask is, how does this high energy electron or Hall excitation fractionalize into the fundamental objects which are composite fermions? Okay, so the thing that is going to happen is this tunneled electron is going to be a tightly bound state. So why tightly bound state? Because the electron is going to be created locally under the tip. So at a position R, it has to be a tightly bound state because there it's an electron. So if you look at filling factor n/2n+1, in general, the electron splits into 2n+1 composite fermions. So for example, if you look at 1/3 Laughlin state, then the electron is made up of 3 composite fermions, each of which carries a charge E/3. So a single hole or a single electron excitation is going to be a tightly bound state of 3 electrons or 3 composite fermions here. Okay, so first thing that we always do, if you can do exact diagonalization, you just do exact diagonalization. So one you can do quickly is to compute the local density of states for removing or injecting an electron at the north pole. So in the Landau level, there is this nice feature that position and momentum are connected. So if you tunnel an electron locally at the north pole, which is this angular momentum q, that is also local in space. So you're going to put an electron in this topmost orbital near the north pole at some energy E. Okay? So that amounts to either removing an electron from this orbital minus q or addition of the electron at orbital q on the ground state. Then you look at the sum over all eigenstates. So now the other thing we are going to do is to use the composite fermion theory to capture the same signal. So we are going to assume that there are 2n+1 composite fermions. Okay? So we are going to do this so-called thing called composite fermion diagonalization, where you take 2n+1 particles or holes at the effective magnetic field and compute exactly the same signal. So now you're going to take states of composite fermions which have 2n+1 particles or 2n+1 holes. And then you compute overlaps with the electron and hole excitations. And then again, this process is basically like you do ED in a reduced subspace. And this subspace is made up of composite fermion states. So the first thing to check is whether this subspace is going to agree with what exact diagonalization gives. And the answer to that is yes. So we first get excellent agreement between exact diagonalization and composite fermion theory for the local density of states. I mean, this is somewhat surprising because you would have thought that composite fermion theory is some low energy effective theory, so it captures the low energy physics properly, but it may not capture some very high energy states well. But it turns out that it does. So this came as a surprise. So here what I show is that the orange lines are the local density of state signals from exact diagonalization. And these blue lines are the local density of states from composite fermion theory, which is done in a much reduced Hilbert space. And the thing that we are going to use is this fact that if you now match exact diagonalization with composite fermion diagonalization, you can now say that composite fermion theory works well to compute the local density of states. And then you can go ahead and use this fact that composite fermion states can be constructed for very large system sizes and just compute local density of states from composite fermion theory for very large sizes. That's what we're going to do. But let me first say that you do this at many fractions like 1/3, 2/5, 3/7. And basically the orange line sits right on top of the blue line. So exact diagonalization is well represented by the composite fermion theory. So if you look carefully, you will notice the following. So if you look at the whole sides, which are the negative energy states, then the agreement is actually much better than it is on the particle side. So I'll explain why that is the case. The reason is that the particle side has to be necessarily truncated. Why? Because if you have, let's say, some Landau levels and you add some particles, the particles can go to very high Landau levels, right? Particles can go all the way up to infinity of Landau levels. You have Landau levels available all the way up. There is no limit to what is the maximum Landau level to which you can add particles. So in all these computations, just because we can compute only for some finite number of levels, you make a truncation where you say that you're going to compute up to, let's say, 7th Landau level or 6th Landau level and so on. So that's why unlike the whole state, the whole only resides within the first few Landau levels. So you can capture that exactly. But the particle can go very high up. So that's why on the particle side, one always has to do some truncation. And that is always going to miss some states. But of course, the agreement can be improved if you keep adding more and more states. Because eventually, if you keep adding more and more states, you're going to hit the Hilbert space, maximum Hilbert space. And there we know the agreement is going to be exact, because then you're capturing the Hilbert space fully. So, okay, so now let me explain what these peaks are and how do we get them. So the first case that we're going to take is, let's say you are in the Laughlin state and you place a single hole at the origin. So the tip is right above the origin and you're removing an electron from there. So it's very easy to show that on the Laughlin side, there is only one unique state that you can write down, which corresponds to this putting 3 quasi-holes at the origin. Right? It is a tightly bound state of a single hole at the origin. And that in the Laughlin language is this unique state. You take the Laughlin state and you do product I less than product I zi to the power 3. So if you didn't have this factor of 3, it will produce 1 quasi-hole. But to make a full hole, you need 3 of the Laughlin quasi-holes. And this is the only state that you can write down. And this is precisely the peak that you see. There is only a single peak. And it's at a particular energy, which is the energy of this state. That's all. So this is like you take on the sphere, this means you take the last 3 orbitals of the North Pole and empty them out, and then you just create integer quantum Hall state of that, and then you Jastrow attach with 2 vertices, that's all. Okay, so in general, what can happen is that you can get multiple peaks. Okay, so how do we understand these multiple peaks? So on the whole side, we saw that there was only 1 peak, but on the electron side of 1/3, you see 3 peaks. So how do we understand that there can be 3 peaks? So what you can have on the electron side is you can have 3 quasi-particles that can go to different lambda levels. So the lowest lambda level is always occupied. Now I can put 3 quasi-particles in this configuration or this configuration or this configuration. These 3 configurations have different kinetic energy of composite fermion. Right? Let's say if I call this configuration kinetic energy 0, then this has 1 more particle in a higher lambda level. So this has kinetic energy 1. This has kinetic energy 2. So now you arrange all possible ways of 3 particles in a given kinetic energy, and you see these peaks. So kinetic energy 0 is this peak, kinetic energy 1 is this peak, kinetic energy 2 is this peak. And then higher and higher kinetic energies are like suppressed, so you see smaller and smaller peaks there. So in principle, every peak here corresponds to one particular kinetic energy of composite fermions, and that's why we call this as a fingerprint of the composite fermion lambda level. Because every lambda level of composite fermions corresponds to a particular kinetic energy. So now you can work this out in general for any fraction. So here are some examples of 2/5 and 3/7. So in 2/5 on the whole side, you see like 3 peaks roughly. 2 of them are very strong, third one is not so much. On the particle side, you again see many peaks. On the 3/7 on the whole side, again you see many peaks. And all of these peaks you can arrange by just kinetic energy of composite fermion. That's what I'm going to show next. So here are examples of 1/3, 2/5 and 3/7. So these black lines are when all of the peaks are put together. Okay, and then these blue line is for kinetic energy corresponding to 0. Red line is kinetic energy corresponding to 1, and this blue line is kinetic energy corresponding to 2. So you now just, instead of taking all states, you just take states with a particular kinetic energy, and each of them reproduces 1 peak. So each color basically reproduces 1 peak. So each local density of state peak corresponds to a particular CF kinetic energy. Okay, so as I said earlier, the whole state is fully captured. So if you look at what is the overlap of the electron or whole state, of the whole state in a given fraction, in terms of the CF state, then that whole state has overlap 1. Whether you do this at 1/3, 2/5 or 3/7, because if you are at, let's say, 2/5, the whole is within the 2 Landau levels. So everything within this space will be captured by composite fermion theory. But on the particle side, we'd never capture the full state. So let's say, for example, at 1/3, we capture like 80% of the state up to the truncation that we have kept. And at 2/5, this is worse and worse. But qualitatively, it seems like the amount of truncation that we have imposed is sufficient to capture whatever is needed. So there's also a simple model that one can write down, a phenomenological model that was written down before we did all these computations. And this was done by experimentalists. So what they suggested was you can simulate this signal with a very simple model. where you say that the higher EK states are higher order processes and their contribution to the STM signal is suppressed. So you take a model where the intensity is the number of states at a given kinetic energy times some phenomenological parameter T to the K, where T is some number that's smaller than 1. And then you take the signal and fit and then see how well that reproduces. So that signal is, so this model numbers are given by these red lines, and they actually do a fairly good job of picking out the signal. Okay. But if you look very carefully at details, then you can see that there are some mismatches. So for example, if you look at filling factor 3.7, the first peak is actually lower in intensity than the second peak, whereas that's not the case in this model. So there are some details that this model misses out, but it does a fairly good job. And the reason for this discrepancy is that in general, actually the composite fermion basis states are not orthogonal. So if you, let's say, take composite fermion basis states for some given cyclotron energy, like 3 h bar omega c star, then it contains everything below it also. So the 3 cyclotron energy of composite fermions contains 2, 1, and 0. So what you are supposed to do if you want to get the signal for 3, you have to re-orthogonalize with respect to all these ones below. And that is not done in this model, right? Where you just compute how many states are there at a given k. So that is what this misses. So what about finally the signal comparison against experiment? So in experiments, it is indeed true that multiple peaks are seen, but their numbers and energies actually do not match our theoretical prediction. So the case to compare against is 2/3 on the particle side, which is like opposite of 1/3 hole. So there we can see one very clear peak, but there's also another peak that shows up. Okay, so that is missing in our theory. On the whole side of 1/3, we have only one peak. So the belief is that this mismatch is probably because the tip is not very localized. I mean, although they claim from the experimentalists is that it's very localized, it may not be like super localized. And also the tip is like some metal, so it actually screens the interaction. Whereas everything that I told you up until now was to take the ideal Coulomb interaction. There is no screening done. So probably one requires to do a better modeling of the tip to capture these features, which we are missing out right now. Okay, so outlook. So one age-old problem that we've been like bracing ourselves with for a long time is, can we tell what is the topological order of the phi-half state? So this phi-half state is believed to be non-abelian, and many motivations for quantum computing, especially topological quantum computing, have come about because of this phi-half state. So there are multiple candidate states that have been written down, like Pfaffian, anti-Pfaffian, pH-Pfaffian, and so on. So all these, all the experiments that are in favor of either of them is usually an edge measurement, whereas an STM is a bulk measurement. So is it possible that if you manage to do an STM on this state at phi-half, you will be able to uniquely identify the topological order? So that is one interesting question that one can answer. Then one can ask this general question, how does STM see some signatures of partonic structures? So this is not restricted to just quantum Hall, but you can ask this question for spin liquids and so on. Okay, so to summarize, the STM signal can serve as a unique fingerprint for strongly interacting topological phases of matter, and it thereby opens a new direction for studying fractionalized excitation. And in principle, it can identify uniquely what is the many-body ground state. So let me end with that, and thanks for your attention. So some part of the fingerprint was because this looks like fingers.
Hey, thanks, Ajit. Questions? Yeah.
Yeah. So that's what is done in this paper. So that is very hard for us to do numerically because of this fact that there is no gap. So you can never truncate up to some level and compute, right? And getting a gapless Fermi liquid on, let's say, the sphere and so on is a really hard problem. But it has been calculated with this Chern-Simons theory that I talked about, which Adi Stern and his student have done. And what they find is that these discrete peaks that you have at these Jan fractions, they go into a broad continuum as you approach 1/2. So there are these unique discrete peaks disappear and you get a broad continuum.
Thanks for the very nice talk. How do you say that the contribution is coming from the complex fermion instead of just simple fractional electrons can give 1/3 of an electron instead of a combined 1/3 of an electron with the fluxes and all?
I'm saying that every electron is made up of 3 of these composite fermions. An electron has to be made of 3 of these because the charge has to add up. So if you have an electron, it is a charge E object. And you cannot get that from a single composite fermion. A single composite fermion is a charge E with 3 objects.
I'm saying separating the 1/3 of an electron with the fluxes. How are you saying that they both combine to give this contribution?
I'm not saying anything like that. So I'm just saying that the electron itself is made up of 3 composite fermions. A composite fermion is an electron and 2 fluxes. So now I'm just saying that the single electron is made up of 3 composite fermions.
Would it make a difference if you would consider optical spectroscopy, for instance? You would make similar kind of transitions.
Yeah, yeah.
Why haven't people done this before? Because optics is so great in measuring.
Yeah, my understanding from the optics community is that it's hard. That's all. I don't know exactly why. And they're also worried a little bit about like this thing called wave vector conservation, because you shine. So then here I'm assuming that the momentum is conserved, and I do everything assuming that they believe is broken. And yes, that's the main reason.
Thank you.
Could you say a little bit more about the experiment to which you were comparing? This is presumably monolayer graphene.
No, this is bilayer graphene in a particular Landau level.
Oh.
So you project onto the n equal to 0 Landau level in bilayer graphene with a given valley and spin. So it's effectively like monolayer graphene.
Do you have to make an assumption about what is the underlying order for that?
Yes, so I mean experimentally they don't, but we are making an assumption that it's all fully polarized in a particular valley spin and so on. We don't allow for any fluctuations in that degree of freedom. The computations assume that. They assume single component ferromagnets and that's all.
So is it possible that your discrepancy is from there?
Yeah, that's a great point. So it is possible. Yeah, it's possible. We haven't tested that out.
In your outlook, you mentioned 5 half states, right? So that's not really seen in any of the graphitic systems.
No, bilayer graphene sees phi half, but STM hasn't been done yet on it. Detailed STM measurements haven't been done yet.
Any other question? We have time for half more. I just wanted to have a very quick question about the experimental aspect. When you are trying to do STM, there is always going to be a bias between the tip and the sample. So intrinsically, these are non-equilibrium measurements.
Yes, yes. So there is always some finite gap, and on top of that, there is this gap of the state. So that they measure by that they are able to, they go to some known state like nu equal to 1, where you know what the gap should be, because every excitation has to be cyclotron energy. So that they subtract. And then this is the gap that you get post that subtraction. And I'm assuming that that gap holds everywhere independent of what is the underlying state. So that is also an assumption.
All right, good. If there's no other question, let's thank Ajit for a very interesting talk.